I'm Palma, as I was presented, and today I'm going to talk about a very cool research that I've been working on in the past few months. But I'd like to start by telling you a quick story that I think most of you already know about. So on July 20th, 1969, the humans first managed to step on the moon. And it's 2025 right now. It's been more than 50 years, so why have we not gone back to it? So we have improved our technology. Actually, in a smartphone right now, we have more technology than there was in the Apollo 11 mission. And we have also improved our safety in space travels. But we also have to make sure that that mission is worth it financially. So the Apollo 11 mission that landed on the moon costed $350 million at the time, which would be worth around $4 billion right now. And here's the big problem, right? We want to go outside Earth, we want to build cities, we want to create a civilization outside of Earth, and we want to go back to the moon. But the big problem is that it costs $1 million per kilogram to take materials to the moon. So just to get 1 kilogram from Earth to the moon in a spaceship, it will take us $1 million. And that is a lot of money when we're talking about building a whole house in the moon. To build, a simple house, it would be $50 billion just to take the materials from Earth to the moon. So as you can see, that's a big problem. And what I thought to myself is, well, why are we looking at taking the materials if we have the whole moon to build with? So I know you might be thinking, right, Palma, what are you going to be building in the moon? There's only big rocks and dust. So we cannot build with the big rocks because you would need huge machines to actually move them and build with them. But we can build with that dust that's all over the surface. And that's exactly what I've been working on. The topic is using carbonic anhydrase enzymes to develop cement through lunar regolith. And this is going to be saving up to 70% of the energy compared to other methods that we have right now on Earth. So first of all, let's clear up a few things, right? Because I've been talking about going to the moon, and you might say, well, right, we're in Cambridge. I can go outside on Earth and have a picnic on the grass. I can walk my dog. Why would I even want to go to the moon in the first place? And apart from it being very cool, there's also two main reasons by which we want to do this. First one is, if we're able to build on the moon, which is basically a desert, there's nothing to build with in there. We will be able very easily to build in places that are dry and very arid on Earth. And that is a great benefit for the people who might be living in these areas. Because imagine having a machine which is 1 meter squared in size and being able to make a house out of it with nothing else. You don't even need water for it. The second reason is that we are facing a possible future climate catastrophe. And even though our main goal right now is to solve that problem here on Earth, and there are many great people, including me, who are working on different projects to try and solve it, we're seeing the problems with it right now, day to day. And we need to have a plan B in case there's not an option to save Earth in the long-term future. So we need to be able to be able to leave Earth and build outside. And the first step for that is our own moon. It's a utility that we know very well. We know the conditions and we know what we can do in it. So now that we know a bit about the why, let's talk about the star of this research, which is the module Selene. And Selene is a bioreactor. This is the full module, and the goal for this is to be flying with Artemis mission of NASA in mid-2027. But it basically consists of 2 bioreactors. It has a bioreactor alpha and bioreactor beta. In the bioreactor alpha, you put H2O and CO2. This H2O and CO2 is taken from the first bases that Artemis is planning to establish on the moon, and they will be taken from recycled CO2, recycled H2O from astronaut activities, normal in the base. The quantities needed are minimum, so you don't need to bring any bulk water from Earth, it's just vapor. You put them in the bioreactor alpha, as well as some carbonic anhydrase enzymes, which are going to be immobilized in a silica plate or some other medium. And there is where magic happens. So in there, you're going to produce carbonate. And then that carbonate, that reaction is going to be catalyzed by those enzymes in the bioreactor alpha. It's going to travel through a microchannel, which you can see right here on the screen. I can point, onto the bioreactor beta. And in the bioreactor beta is where we're going to introduce the lunar regolith in. This is going to be the dust, which we can find on the surface of the moon. We put it in, and it's going to, as well as with calcium ions, which we can also find in the soil in the moon, it's going to produce calcium carbonate. And this calcium carbonate, under low humidity conditions, is going to form precipitation and crystallization, which is going to solidify that lunar regolith into actual cement. So it's going to be solid in the end. And here's a bit more of a detailed overview about this solution. So as I said before, we're going to have the enzyme carbonic anhydrase immobilized through mineral support. That could be silica gel or zeolite as well. The bioreactor uses a technology that I named LDU, which is lunar dry enzymatic welding. Is basically what we talked about. The bioreactor does with the enzymes to produce the lunar concrete in the end. And the input materials is just going to be the lunar regolith and then the calcium source, which can be the soil itself from the moon. It's going to be in a controlled atmosphere at the beginning. So in the bases that are going to be put, temporal bases from Artemis, is going to have CO2 and minimal moisture, as you know, because in the moon we're not going to have that. And there's going to be the enzymatic reaction with the carbonic anhydrase catalyzing the conversion of CO2 and water vapor into the bicarbonate, and that bicarbonate is going to accelerate the precipitation of the calcium carbonate in the end. What it's going to produce in the end, the result is an in situ dry consolidation of lunar regolith into this strong cement that we can use to build the first structures on the moon. These are some of the external designs for this Selene module. The name comes from, NASA has the Artemis mission and has the Apollo mission. So Selene is a Greek personification of the moon in Greek mythology. That's why we chose the name. These are made in Tinkercad and Blender and are the initial designs. Right now, I'm in the process of designing new ones with the updated module. And there are other solutions right now in terms of what is going on with the construction on the moon, but they all have many limitations. So we can go through them right now. The first one is geopolymers. And geopolymers is a method that uses lunar regolith and uses strong chemicals and alkaline especially, such as sodium hydroxide and sodium silicate, to produce a cement-like material. The problem with this is that you need a very large amount of water. And the problem with the water is the same problem that we have with bringing materials from Earth to the moon. It's that it's very heavy to load, and that costs a lot to get into a mission. And you might be thinking, well, can we not get the water from the moon itself? And that's a good idea, because we have iced water, so fully frozen water in the poles of the moon. But you would need huge machinery to actually excavate in those poles of the moon to get the water out and then melt it. So that would require a lot of energy as well, as you can see. Not as much as for the other solutions, but still a lot of energy. It's not really scalable. You need a lot of water, a lot of resources. You need to bring those chemicals with you from Earth as well. You need to bring that sodium to actually be able to produce the geopolymers. And it also drops its performance under vacuum and thermal stress, which is a condition that is constant on the moon, so that is another big problem. Another solution right now is sulfur concrete, and it's basically sulfur-based lunar concrete, but it mixes molten sulfur with lunar regolith to form a concrete that does not require water at all, so that's a plus. The problem is that it's sulfur, when you put it under vacuum conditions, it sublimates, so it basically evaporates, and that gas is very toxic. So you would have to have that procedure done in a place completely separate from where the astronauts are living, and there is the risk of leakage, so it's very dangerous to have. You would also need a sulfur-rich location to do this on the moon, and that's not everywhere. You would have to land in those specific places, which would add complications. So it is not a great alternative. It's also not really scalable because, again, you would need that heavy machinery to bring. You will need the chemicals, you will need everything. And another major technology right now is microwave sintering. And this one is one that I personally like. So this one is you are using a lot of radiation, so microwaves, to fuse regolith particles together. But you can imagine the amount of energy you actually need to melt the lunar regolith and fuse those particles together. That is a lot. And for that amount of energy, you also need to bring a very big machine to actually melt it. You need a lot of energy. Even if you're using solar energy, it would be a lot. You would need supplementals, so you would need to bring from Earth. So that is a problem, and it also adds to the cost. Every single time we're adding energy used, you're adding to the cost. There are also other methods that use living microbes, like MCIP, microbial-induced carbonate precipitation. And these are some of the ones that the European Space Station are considering right now. So the microbial-induced carbonate precipitation uses live bacteria, and they bring it there. The problem with bacteria is that they are living organisms, so they need water to live. And water is molten gold on the moon. It's super valuable, like we said. You cannot get it everywhere. You need to bring the water with you, or you need to bring a huge construction machine, and I have never seen that in a spaceship, so I think it's for a reason. Also, ESA, the European Space Station, is right now working on other methods such as 3D printing. So it's basically a huge 3D printer machine on the moon, and they are trying to build surfaces from that. The problem with that is, first of all, you need the machine there. Second of all, you need a lot of water too, and that water, like we said, is very hard to get there. So the only method that does not need at all water taken from Earth, it takes it all from the one that we're going to have in the basis, and it's also very low energy use because we're using enzymes for it. We're not bringing the bacteria from Earth to the moon because you would need to conserve those bacteria, and you would need heavy shielding for them. So we're only bringing the enzymes, and the enzymes come in small capsules depending on the amount you need. You don't really need a lot. It's very small capsules that you need to bring. And they do not require very specific conditions to live in. They can survive. So again, no water, no external heat, no imported chemicals, and no bulky hardware needed. And there are many benefits to this solution. So the main one is that it saves $500 per mission. So it eliminates the need to send materials from Earth, and it reduces launch mass by 70% and reduces the energy as well by 70%. So this cuts the CO2 and the water waste by up to 80% as well. And it uses closed loop biocatalyzed chemistry, so that's a plus as well. Now we have great plans for the future, and the main one is that in the first 2 years we're going to have a working module prototype working. It is going to consist of developing the enzyme formulations in a lab procedure, make sure they work under lab conditions, which are ideal conditions, and then testing the regolith solidification under simulated lunar conditions in a lab. By year 3, we're going to have tested this module on the moon. So the main goal for this right now is for it to fly with the Artemis 3 mission in mid-2027 and to do its first testings on the moon on mid-2027. So that way we're going to be able to demonstrate, the large-scale biocementation and actually produce that cement through lunar regolith. The first test, of course, will be through regolith in very dry areas that have a similar chemical composition here on Earth, but by year 3 we're going to be testing this on the moon. And by year 5 we're going to have expanded already. So we're going to deploy LDU, lunar drying somatic welding kits, for ISRU, which are in situ resource utilization missions to scale this construction systems. And we're going to be collaborating with ESA and NASA all the way through. But in total, it's going to be reducing costs by over $49 billion per structure that is built. So remember I told you it was $50 billion just to build a house on the moon. We're going to reduce it by $49 billion. And it's going to make building on the moon possible a full decade before other current technologies are ready right now. We're basically tackling the hardest engineering problem that humanity has ever faced. And it's the first step to build the civilization beyond Earth, because we have to first step on the moon with nothing but dust and science and of course a whole lot of determination. Thank you very much, and I invite you to check the LinkedIn for real-time updates on this project.
Really, really exciting presentation. Thank you so much. Shall we start off with some questions from our audience? I can go first. I cannot underestimate that when you said that it's one of the most complicated things we have ever done, because I was reading an interesting statistics. Apollo 11, or when we sent humans and we wanted them back alive, the single point failures was around 2025.
Yes.
But the last biggest deployable mission, which is the James Webb Telescope, the single point was 500. To get just the machine out, properly deployed, the cryo thing and works properly, it's super complicated apparently. So yeah, I can appreciate, I'm super eager to look forward how it unfolds. So any more comments on any hidden things that you have left out of PPT that we should know in the upcoming years?
Well, in the upcoming years, I think this is going to be huge because, well, you know, the main purpose of this is to have it in a long-term future as an alternative, but it's going to be useful in the next 2 years. We're going to have the working prototypes, right? And in 5, it's going to be already generalized and it's going to be able to be used. Here you can check my bibliography of 3 pages. It's as well in a QR code. And well, yes, I think it's going to be a very big step. Again, because it's not about living Earth and giving up on it in a climate crisis. It's about focusing on both sides, focusing on Earth as well, but having this as an alternative in the long-term future to be able to go to the moon. And it's true that it's a very hard thing to do, but this is going to reduce the main problem that we have right now, which is the financial stability in terms of actually sending all those materials that we need.
So Palma, so the calculation that I was looking for in your presentation, and it wasn't there, but perhaps you've done it, is the volume of water and the carbon dioxide that are
Yes.
needed for the carbonic anhydrase reaction to make like a single house.
Right.
So
Yes.
So I presume that the carbon dioxide comes from the astronauts who are breathing out the CO2.
It does.
And then it's being captured, or is there another source of CO2?
The main source of it is going to be from the Artemis bases. We're going to be, yes, produced from the astronauts. It's going to have capture detectors inside the bases, as well as for the water vapor. So in talking itself, we're going to take it from residues as well. Another carbon CO2 source that we're exploring right now is the soil itself, because it seems that we can take some from it too, while in the process of doing the, inside the bioreactor, especially bioreactor alpha. So we're trying to get some from it right now too. The amount of water vapor is, in the rough calculations that we have done. So right now we're in the process of testing. We're in contact with the NASA Jet Propulsion Lab. We're going to start doing tests on what the actual amount will be. The rough average that we have right now is less than half a liter to build a house of water vapor, and CO2 it would also be a very low number, not specified yet because we have not enough information. We need to do tests.
So how does the mass calculation go, though? If it's less than half a liter of water, you cannot make a ton of calcium carbonate from half a liter of water.
You can, because the reaction is going to be, so the enzymes are going to be in a silica gel plate, and you don't really need, for the reaction, while using the enzymes to catalyze it, the calculations we've done, like in theory right now, you don't really need that amount of water. You can use that amount of water vapor to actually use it.
But we can talk offline.
Yes, of course.
I also feel some chemistries of half a liter of water, a little bit amount of the other initial, but the output we are expecting quite a lot of carbon. Okay.
The big amount comes from the regolith itself.
I have a few more questions. My PhD is in carbon capture, so using materials. Great. Oh, fantastic. Please go ahead.
So, how are you going to test your technology? You will bring the material from moon to Earth, or you will go to moon and test it?
So the first tests that we're planning to do are not with lunar regolith, but we're going to be using soil that we can find in dry places on Earth that has a similar chemical composition to those on the moon. And we're going to try on Earth first. Once we can confirm that it does work on Earth, it works in theory, once we can confirm it experimentally, then in a few years we are going to be actually sending a module to the moon and testing it on the moon with the materials on the moon. Yes?
Yeah, so you mentioned how we could use this technology in like arid climates on Earth as well.
Yes.
So I imagine the process becomes much more easier since we are on Earth. How does it change in any way?
It would only change in terms of the maintenance of the enzymes. So while you don't need as heavy shielding for the enzymes as you would need for bacteria on the moon because of vacuum, you would need some sort of shielding first of all on the way up, and also like it would need to be inside the Artemis bases in the moon. On Earth, you don't need that. The enzymes would not denature under usual Earth conditions, so that would be much easier. You also don't need to account for radiation in the process, which the module itself is sealed for radiation. There's no problem with that. But while the astronauts are working on it, you would not need to account for that radiation or for the drastic change in temperature as well.
Can I add one question to the output? Are we looking at similar concrete on Earth? Should we account for anything more radiation, more tremors in moon or something like that? The fundamental material?
Yes, the final fundamental material what we have in mind is something very similar to how cement looks right now on Earth. It would be, though, more prepared for radiation in the future, because something that we need to take into account right now is that how it is going to be able to hold onto, after radiation, not in the first days, but after 15 years it needs to still hold up. So it might be harder, it might be more resistant in the end. The form, like physically itself, it should be very similar to how we see cement right now on Earth.
Thank you. Please go ahead.
I was wondering about the social implications of such a project. So, who would be leading this project, and in terms of accessibility, what is the vision as well? And yeah.
Yes. So the first people that would go are, of course, scientists, researchers. Actually, we would be implementing this. We wouldn't be making a whole new mission. It would be implemented into the Artemis mission that NASA already has. So it would be the researchers that go into that mission that start testing it. Of course, not us going to the moon. It would be scientists, professionals, and in a few years, once this is generalized to public, or once we have space travel as more common, then it would just be normal people that would be able to go to the moon once that is also working in other different missions, not only for this one. And to who is leading the project right now, I'm working on it right now, but I'm working with many experts from NASA and ESA as well. So once this starts being implemented into their systems, of course it will be collaboration between the space agencies.